What would be the best unit to mass high school students in? No, it's not kilograms, it's Instagrams. Hey guys, let's start talking about nuclear reactions. Protons and neutrons in the nucleus are held together by nuclear forces. These are often referred to as strong forces. But they have to overcome the repulsive forces of the protons. Protons are positively charged, and likes repel each other. So the protons are trying to push away, but what's holding it together, these attractive forces or strong forces, is what's holding it together. I often think of it like gravity. The masses attract towards each other, and really the mass of everything is the nucleus. The nucleus of the atoms is what makes up the mass of who you are. So this is where all the mass is. So inside of an atom, these nuclear forces or strong forces are holding these protons and neutrons together. But at the same time, we have repulsive forces in the nucleus. We have the protons trying to get away from each other. So within an incredibly small space, you have the two strongest forces in nature pitted against each other. The strong forces are pulling everything in, while the repulsive forces are pushing everything out. Again, the strong forces or the nuclear forces is the mass. The mass is attracting to each other, where the repulsive forces are the fact that these protons are positively charged and they're trying to repel each other. When this balance finally breaks, an enormous amount of energy gets released. And this is what we call nuclear reactions. Nuclear reactions give off radioactive energy. At about 84 nuclei, the repulsive force overpowers the nuclear force. So that means what's being pushed apart starts to overcome the attractive forces. More and more neutrons get added to try to compensate, to try to pull things together, but the repulsive force starts to win after about 84 nuclei. Nuclei means anything in the nucleus, neutrons and or protons. And so after 84 nuclei on your periodic table, you'll start to notice more and more radioactive elements. Now, when the balance breaks, we get different types of radiation. What can happen is when the balance breaks, a piece breaks off of the nucleus. And when the piece breaks off where it's two protons and two neutrons, this is called an alpha particle. An alpha particle is two protons and two neutrons, and it literally breaks right off of the nucleus, gets released. That's a type of radiation. And yes, two protons and two neutrons makes up a helium nucleus. There's no electrons here, so it's just the nucleus. Sometimes an electron can be broken off. This is called a beta particle. But what's important to note about this is this electron is being broken off of the nucleus, and we'll talk about how that happens in a moment, not the electron cloud. So we're not talking about an electron being removed from the normal electrons. This electron came from the nucleus. And you should be wondering, where did the electron come from? Because there are no electrons in the nucleus, and you would be right. That's a good thing to think about, and we're going to talk about that in a moment. The last type of radiation I want to mention, these are the three most common types, by the way. There is different types of radiation, but these are the three that I really want to focus on, is gamma rays. Gamma rays are very, very high energy electromagnetic waves. There is no mass with a gamma ray. It's basically very, very high energy light. Think of it that way. The different forms of radiation have different penetrating powers. So I'm going to use an example here of some different things, materials that we're going to talk about the penetrating powers of. So let's take a look at some paper, wood, and concrete. An alpha particle is the heaviest of the different types of radiation we mentioned. It's got two protons, two neutrons, and it can be blocked by a piece of paper. Your clothes could block an alpha particle. So if you're exposed to alpha radiation, you could get radioactive burns perhaps on your skin, but your clothes would be protecting you from that. It wouldn't be able to penetrate that. A beta particle can go right through paper. Remember, this is an electron. It can go right through paper, but it can be blocked by wood. So if there was beta particles being released by radiation, you could be pretty safe inside of your house. A gamma ray is an electromagnetic wave. It has no mass, and it can travel penetrate through anything. It penetrates through paper, wood, and even concrete. So let's talk about alpha radiation. An alpha particle is composed of a helium nuclei. It's got a positive 2 charge because there's no electrons, and it's got 2 protons, and it's represented with the lowercase Greek symbol alpha. If uranium-238 undergoes an alpha emission, it will produce, of course, an alpha particle, and the alpha particle is represented like this. It's helium because it's got 2 protons, but it also has 2 neutrons, and 2 plus 2 adds up to 4. Remember, this is the atomic mass, which adds up the protons and the neutrons. This is the alpha particle. What you have on the right of a yield sign has to add up to what's on the left of the yield sign. So let's take a look at this number. If the atomic mass lost 4 and it started with 238, the daughter of what's being produced here will have 234, because 238 minus 4 will be 234. And the atomic number, if it was 92 and it lost 2, would have to be 90. If you look on your periodic table, element 90 is thorium. And again, it's 234 because 4 plus 134 adds up to 238. 2 plus 90 adds up to 92. This side, the right side, will add up to what's on the left side. Mass will be conserved. So uranium-238 will decompose into thorium-234 and an alpha particle. This is what you would write the equation for what we're talking about here. Note that when the atom loses an alpha particle, the atomic number lowers by 2. So when you undergo an alpha emission, you would subtract 2 from your atomic number, which makes it a new element. So if you subtract 2 from 92, you gotta look on your periodic table, you find that element 90 is thorium. And you also subtract 4 from the atomic mass, and then you write your alpha emission. Beta radiation is interesting in that what happens in a beta emission is a neutron in the nucleus will break into 2 pieces. It'll release a very small negative charge, an electron. But if it releases a negative electron, that makes the neutron positively charged. So what happens in beta emissions is a neutron releases an electron, but what's left over is a proton. Remember, protons and neutrons have pretty much the same mass, and electrons have pretty much no mass. It's very, very small, and it's a negative charge. So this is what's happening when you have an beta emission. You have a neutron becoming a proton and releasing an electron. And this, again, this electron came from the nucleus. So the formation of a decomposition of a neutron is beta radiation. So a beta particle has a -1 charge, and it's represented with the lowercase beta in Greek letters. This is an example of a beta emission. Carbon-14 releases a beta particle, which has got an atomic mass of 0, it has no mass, and it's got a charge of -1. And what does it produce? It's going to be producing nitrogen. Now remember, if you take a look, a neutron turns into a proton. So the mass stays the same. So if it started off as carbon-14, it is still going to be 14 with this daughter. But one of the neutrons became a proton. So what happens is from 6, what's just carbon, you go up to 7, and then you look at your periodic table and you see that that is nitrogen. So when you undergo a beta emission, the atomic mass stays the same. So the atomic mass stays the same. Beta particles are very, very, very light. They're very small, so it's not really changing the mass. But the atomic number increases by 1. So your atomic number is increasing here, and that makes it a new element. That's what you have to remember for beta emissions. The atomic mass stays the same, the atomic number increases by 1, and you get an electron released, a beta particle. When we have gamma irradiation is very, very high energy electromagnetic waves. Light is also an electromagnetic wave, but much, much lower energy. Gamma rays have no charge, they have no mass, and they have very high penetrating power because of this. So it can penetrate organisms very easily. Lead and concrete can partially shield from gamma radiation, but it doesn't stop it. Again, it doesn't stop it, it shields, it weakens it, And again, if you have enough concrete, you have enough lead, you can weaken it to a point where it's not going to hurt organic systems, and you can even lower it to enough where it starts to become very, very difficult to detect. But it doesn't stop. You're not going to stop a gamma ray. It's always going to be moving at the speed of light. It's often emitted along with an alpha or beta particle. So if you have alpha emissions or beta emissions, and there's a lot of radiation involved with that, you can also emit a gamma ray. If we look at the example I gave before, we have uranium-238 producing thorium-234 in an alpha particle. An example of how gamma rays can be produced, it would be along with an alpha or beta emission. So you have an alpha or beta emission, and if it's high enough energy, you might also get a gamma ray. So the fact that there's a gamma ray released does not change the equation that you're going to be writing. So here's some practice problems that we're going to go over. It's in your evidence notebook, and if you want to pause and write these down, otherwise you can go on to mrras.com and print out the evidence notebook, and you'll have these here. But from what we talked about now, I'd like you to try, you can pause the video right now and try to answer these questions here.
Okay, so let's take a look at this question here. We're going to write the equation to represent the decay of radium-226 by an alpha emission. So what we're going to do first is we're going to start off with what we have. We have an atomic mass of 226, and we have radium, which is the symbol Ra. You're going to look at your periodic table, and if you didn't know it was Ra, you can do this right now. You're going to look at your periodic table and you find radium, which is right here. It's element 88, and so and that's the Ra. So the next thing we're going to do is put that 88 here. That's the atomic number. That's the amount of protons. And it says that the radium is undergoing an alpha emission. So we're going to make an arrow, and I'm just going to put that alpha emission first. An alpha emission is a helium nucleus, has 2 protons and 2 neutrons, so it has an atomic mass of 4, and the atomic number of 2 protons. Plus, what does it become? Well, if it has 226 for an atomic mass and it lost 4, you're going to have left over 222. And if you had 88 protons and you lost 2, you're going to have 86 protons. But what element is that? Well, let's just go back. And if we had now we had 88, now we have 86 protons. So that brings us over here to radon. So that's radon. So that's Rn. And that would be the answer to the first question. Now, can you switch these two here? Certainly. 1 plus 2 is the same as 2 plus 1. So yeah, you can switch these and it's not going to make any difference. And it looks like a little happy face there, which is kind of nice. Anyways, that's the answer to that question. Okay. Let's do an alpha decay of plutonium-224. So again, let's start off with the atomic mass is 224, and we have plutonium. So let's take a look at our periodic table, and we find plutonium right here. It's element number 94. So we'll go back over here, and we'll say it's element number 94, and plutonium was Pu. It's undergoing an alpha emission, so we'll make an alpha particle here. And if it was 244 as an atomic mass and it lost 4 of them, that would leave over 240. And you've had 94 as an atomic number and you lost 2 protons. That will give you 92. Go back to the periodic table, and what element is number 92? That would be uranium. So element number 92 is uranium. So we're going to put a U here. So it's going to make uranium-240 would be your answer. Okay, this question's a little bit different because in this question we're being asked what is the parent nuclide? So we have the decay. The decay produces polonium-218 and an alpha particle. What's the parent nuclide? So what we have to do here is a little bit in reverse. So we're going to start off with our product, and our product is going to be an alpha particle. So we're going to say 4, 2, helium. That's our alpha particle. And we have polonium 218. So we're going to put the 218 here. And let's take a look at our periodic table for what polonium is. Polonium is element number 84, and it's represented with a PO. So it's right over here, polonium. So let's put that on our paper here. So it's element number 84, and it's PO. Now the question is, what was the parent? Okay, so we're just doing this backwards. So if it produced something with 218 atomic mass and something with 4 atomic mass, then it had to have a total of 222 to start. 4 plus 18 is 222. We have 84 plus 2 protons, so that would mean it had 86 protons. Let's go back to our periodic table and figure out what element has 86 protons, and that would be radon. Radon would be the one, so that's Rn. And so we say Rn. So the parent would be radon 222, the parent nuclide. In this question here, we're talking about beta emissions, not alpha emissions. And so when we do this one, let's recall that a beta emission is when you have a neutron turning into a proton and an electron. That's a beta emission. So one of the neutrons becomes a proton. That's a beta emission. So in this question here, we've got radium 226. So we're going to put 226, and we're going to put radium, which is, again, Ra. We did that one in an earlier example. And the atomic number of that is right here. This is radium. It's number 88, Ra. So we're going to put that on here. 88. And it's turning into a beta emission. And a beta emission is an electron. But it does so by a neutron breaking off a little teeny piece that's negative, making the neutron become positive. So the neutron becomes an electron and a proton. That's what happens in a beta emission. So what's happening is the mass isn't changing. So the mass is going to stay the same. It's just that one of the neutrons became a proton, which means the atomic number increases by 1. So let's look on our periodic table and figure out what element is 89 protons, and that would be actinium. Right over here, 89 would be actinium. So our answer, we would put AC here. So that would be the answer to this question here for beta emissions. Our last example on this series here is going to be plutonium-240 releasing a beta emission and gamma radiation. So it's releasing two things. So let's start off with our parent. We've got 240, and it's plutonium. Plutonium is element number 94, and it's represented with a Pu. So we're going to say it's element number 94, and it's represented with a Pu. And it's going to release a beta emission. So I'm going to say this is our beta emission. It's an electron. And it's releasing a gamma radiation. Gamma radiation. What is it producing here? Now the gamma has no mass. It has no charge, so it's not going to change anything. So it's basically just do what you did with a beta emission and just add the gamma on here. So again, a beta emission, you do not change the mass, but one of your neutrons becomes a proton. So 94 becomes 95. Let's take a look back at our periodic table. Element number 95 is americium. AM. So we do that there. Now, if you were to switch this order, if you put americium first and then a beta particle, then gamma, that's fine, because when you're adding it up, it doesn't matter. So any of these can be in any order you want. So now we've talked about different types of radiation, alpha particles, beta particles, and gamma rays. Let's talk about the speed of the breakdown in a nuclear reaction, because some nuclear reactions happen very, very slow, and so even though they're producing radiation, it's such low levels you might not be able to detect it very easily, and other things happen extremely fast. How it's measured is something called half-lives. This is the time required for half of a sample to radioactively decay to create a new nuclei. So when you have a half-life, each half-life that happens, you get half of what was left over. So half of the remaining sample decays to form another element in each half-life. Let's take a look at this graphically. In a normal graph, we are going to always make sure we have a title. I'm just going to have a general title here for the half-life graph. If we talk about a particular isotope, we might have the name of that isotope up here. We have to always label our x-axis and our y-axis, and we have to scale it properly. So what I have down here is half-lives, just generic half-lives, not a particular time. If you had a particular element, we might have actual time here, but this is just half-lives. So what I'm saying is, in the first, when you have the sample, you have you have the whole sample. So this is a fraction we're putting here. So we have we have the whole sample. In the first half-life, we have half of that sample left over, which would be 0.5. And a lot of people think, okay, well then in the second half-life, then you're going to have 0. It's going to, but what happens the second half-life, you're going to have half of what's remaining. So now we only have this much remaining, 0.5. We're going to have half of that, which would be 2.5. And now we're going to have half of 2.5 on the next half-life. So 2.5 should be around 12.5. So let's just take a guess. I think that might be around here, right? It's less than 1.5 would be here, so this is about 2.5. So I'm going to say it's about there. Hey, pretty good guess. So now we've got 12.5% or 0.125, and we're going to take half of that. So that's going to be roughly 0.06 or 6% left over. So I'm going to say that's probably going to be about here. And then we're going to have half of that on the fifth half-life, so it's going to be roughly 3. So I'd say maybe about here. And then we'll have half of that, which is going to be about 1.5%. And then we're going to have about 0.7%. So it just gets smaller and smaller and smaller. And it's just going to get half and half and half of this. So you can see after 7 half-lives, it's going to get closer and closer to 0, but it's never going to get to 0 because we keep dividing it in half and half and half. So after 7 half-lives, it's rather difficult to measure how much of the sample you have left over. So let's put numbers to those. So things like thorium, an isotope thorium-219, has a half-life of roughly 1/1,000,000th of a second. So if you take a second and divide it up into 1,000,000 equal pieces, that would be the first half-life of thorium-219. So in a complete second, it will have undergone 1,000,000 half-lives. So there's not going to be anything left measurable after a second. That's a lot of half-lives. And it's going to produce an alpha particle. If we go down here, we have carbon-14. This is a naturally occurring isotope. We have some in our bones. But it has a half-life of almost 6,000 years, 5,730 years, and it releases beta particles. Because it has a half-life of roughly 6,000 years, you can go through about 7 half-lives and still be able to measure what's left over. Things that are carbon-based, such as organic material, we can take a look at it. If it's, I would say, under 30,000 years old, we can take a look at how much carbon-14 is left over, and we can determine how old that is. So we're looking at fossils that are maybe 30,000 years old or newer. We can carbon date it. That's what carbon dating is. If it's older than that, we're going to have to use things that have much lower half-lives, and we find those things in the Earth. And we do what's called relative dating, so like dinosaur fossils and things like that. Things like uranium have almost 4.5 billion years as its half-life for just half of it to decay. So these older things, these things that go really slow, help us determine the age of Earth. Now there's 2 types of nuclear reactions. We have fusion and fission. In fusion, what we have is 2 smaller atoms combining together to produce a larger one. So here we have 2 helium atoms, and we have 2 types of common things that produce the helium. We have deuterium and we have tritium. And it's basically helium. Deuterium has 1 neutron and tritium has 2 neutrons, so it's got 3 subatomic particles, and 2 subatomic particles is where it gets its name. They combine together, release a lot of energy, and they make a larger isotope, or a larger atom, and it releases a neutron in the process. So This occurs often in stars. This is what stars are doing. They're making smaller elements into bigger elements in stars, and it requires high density and high temperature environment. So it takes a lot of heat and a lot of energy. So the stars have so much mass that it's actually crushing these smaller things into making larger particles. And then when a star explodes, so then the helium, let's go before we go, the star explodes, the helium will then can undergo fusion and become larger, more complex things, and we can eventually get things like carbon, and we can get things like iron, and we can get things like uranium. It gets bigger and bigger and bigger. The star eventually runs out of the ability to fuse, and the star collapses. And if the star collapses and explodes, that's called a supernova, releasing all those more complex, all those larger elements into space. That's where the larger elements come from. This is where elements come from. It comes from the process of fusion. So yes, technically we are made up of stardust. That's what's going on there. Fission is more common on Earth. This is the splitting of a large unstable nuclei. And it's breaking into smaller ones. So splitting of a large atom into smaller ones. So what happens is you can have a neutron collide into this, and that starts the chain reaction. And as this happens, as it breaks into different pieces, it also releases more neutrons, which are free to then collide into something else. So it starts a chain reaction here. This is the process that's used in most nuclear power plants, and it requires the critical mass of the substance and neutron collisions. So the critical mass means what you're starting with is very large and unstable, so the neutron colliding with it is going to start off this chain reaction. Let's talk about nuclear reactors. Now that we've gone into this discussion here, let's talk about the components of a nuclear reactor. How do we use nuclear reactions to give us electricity? So first thing I want to talk about is in the nuclear core we have things called fuel elements. These are fissionable nuclei such as uranium-235. So uranium-235 is a very common material, very common fuel in nuclear reactors. So that comes in here, and that's these rods. They come in rods of uranium-235. What they do is get a neutron to collide into these rods, and that will start the nuclear reaction. So thermal neutrons collide with the fuel elements to cause fission reactions. And as we just learned, as they collide into there, they break apart, creating smaller pieces and more neutrons to collide back and forth. And this is a chain reaction. Fission reactions produce more neutrons, which then react with more fuel elements. So this is your chain reaction that happens in the nuclear generator. Now the problem is, this is going to go over really quick because every time it collides, it's making more and more neutrons. So we need to slow it down somehow. And so that's where a moderator comes into play. The moderator is a fluid that this is put in, and it's usually water. So it's a substance that slows the neutrons and cools the reactor core. Water is the most common source of a moderator. Control rods are used to regulate the nuclear reaction, and how they do that is they absorb the neutrons so that they can't be reacting with the fuel elements. Control rods can be moved in and out of the reactor to regulate the reaction, and they're often made of cadmium. So the neutrons will get stuck on the control rods, and they won't be able to react with the fuel elements. And so by putting them in, you can slow it down and cool it down, and then you can take them out and get the reaction to go faster. The nuclear core is going to be placed in thick shielding, usually concrete walls, perhaps lead underground, things like this to help protect from the radiation from getting out. So this is going to be sealed up in concrete, so that's shielding. The next thing is, it's going to get extremely hot in here. So to remove the heat of the nuclear core, the moderator is going to move into a heat exchanger. So the moderate is going to move into a heat exchanger, and it will heat up, and the heat exchanger will be water as well. The water will take the heat from the moderator, and it will boil here. Now pay attention here that the water from the moderator is reacting with the nuclear core, but the heat exchanger is not. The water from the heat exchanger is separate. So this water is not radioactive in the heat exchanger, but the heat the water in the nuclear core is radioactive. So what we're doing is we're just transferring heat out. This is not part of the core. That's important to note. We have pumps that cycle the water in and out, and if the pump breaks down, then we can't exchange the heat and the nuclear core can overheat. So often there are backup generators, diesel fuel, that will be used to get the pump working if there was a problem with the nuclear core and there wasn't energy to run those pumps. So we have to have backup to run these things. Once the water boils, the steam will be moved to push a turbine. The turbine spins, which will then spin a magnet with wires around it, which pushes the electrons on the wires, which creates an electrical current. So this can go off into the city to produce the electricity. This is the same principle of a windmill. You just have a windmill moving the turbine, which moves a magnet, which makes the electrons move across the wire. You can have a dam where you can have water falling down a turbine, which pushes it and moves it around. You can have coal. You can heat up water with coal and burn coal. The coal makes steam, and the steam will push this around as well. So this is the basic part right here that makes the electricity. The nuclear reaction is just very hot, and it lasts a very long time, roughly 50 years, of just a massive amount of heat. And we use that heat to boil steam, and the steam pushes the generator. Again, there is no nuclear radiation in this part. All the nuclear radiation is contained in the core.